balance. Although it doesn't technically matter, but usually in this book we go design equation, right? So we don't need to rederive the entire equation for volume. I just erased it. So if we have So does that equation change when I change the problem statement? No, right? Of course not. So we want to rearrange this for what? Right. We can't really do that. These variables are not that easy to separate. So we're just going to partially rearrange, and we're going to get x over 1 minus x squared. And we're going to set that equal to volume CA naught squared. So what am I missing here? K, but instead of just putting K, I'm going to go ahead and just put it in this form. Okay, so that's the equation. And then what's the other equation that we can do? That's as far as we're going to go with the material balance. All right, so let's go to the energy balance. And do we want to write T as a function of conversion? Or is there a better form? Right, we want to write X as a function of temperature. Which remember, we had that. That was the equation that I put on the board where I said XEV. And for this problem, when we remember that delta Cp is equal to 0, and we substitute in, instead of having those summation terms, what you're left with, the heat capacity of A plus B times T minus T naught. Divided by the delta H of reaction times TR. All right, so we have temperature inside this equation. And we have temperature inside this equation. Conversion and conversion. So what do we do?
Well, you should have done it the other way. It would have been so much easier.
No, it wouldn't have been. No.
Plug in X and all those. Iterate until you get T.
Well, yeah, but you got to iterate, right? So what do you do? Huh? So there's a couple of ways that we can do it. There's numerical solution methods, where we set up these things in Excel, for example, and we vary temperature until we vary both temperature and conversion until they both equations are equal, right? Not that hard to do. It might sound hard, but you just set up in your Excel. You set up, this is 1 cell, 2 cells, 3 cells, 4 cells, and then a 5th and 6th cell is temperature and conversion. Obviously, you put in all the formulas, you substitute all the known values, and then you set up another cell, which is just for each equation. You do right-hand side minus left-hand side. And then that same thing for equation 2. And you tell it using solver or goal seek. I think you have to use solver for this one. Vary the conversion and temperature until both of these cells are equal to what? Yeah. Not that hard to do. Take you 5 minutes to set it up. What's another way that we can do it, though? Guess and check. That would take you a lot more than 5 minutes. You guys all have well, not all of you, but many of you have graphing calculators. Why are they called graphing calculators? You can graph them. Is there a graphical solution to this? Sure. Yeah, we already talked about it, right? It's where these two things intersect. So one of these, sorry, not straight line, that's XEB. And then that's the line that you'll get from the material balance, for example. Where they intersect, you get your solution. And like we talked about at the end of the last class, what if they intersect in multiple places? Run away. No, we're going to talk about that. Multiple steady states are in, I think, chapter 12 of the book. Any questions about this problem? Okay, now we're going to talk about equilibrium, which we alluded to start the lecture. But now we're going to come back to it. Anybody know what the temperature dependence of the equilibrium constant is? Or any equations for a rate constant? You could probably derive it that way, but so the equation of name here is, should I get it right? Yeah. Yeah, sorry. That was silly. You guys talked about Arrhenius and it just stuck with me. Okay, and what is big K? Let's say for an ideal gas.
Products over reactants.
Products over reactants.
Where'd you get the delta?
Where'd I get this formula from?
Yeah.
I mean, we're just going to start from this formula. We're not going to go all the way back to statistical mechanics and derive. But essentially, it's just saying that an equilibrium constant is related to the delta H of reaction.
Oh, I see what you're saying.
All right, so we use this little subscript P to indicate pressures, right? That we're writing the equilibrium constant in terms of pressures. So big pi, everybody knows what that is? The product, right? Of the partial pressures divided by some standard partial pressure, or standard pressure, raised to their stoichiometric coefficient. And ideal gas law tells us that the partial pressure is equal to the concentration times RT. So if I want to write this in terms of the concentration equilibrium constant instead of the pressure equilibrium constant, I can, except now there's an extra term. But remember what delta is. Same delta that we've been using. So why is it important to kind of have a handle on both of these? Sometimes you'll be given an equilibrium constant in pressure units. Sometimes you'll be given one in concentration units, especially when you're dealing with gas phase systems. Rates, we write in terms of concentrations, not partial pressures, right? So don't forget about this term. And like I said, this is equal to, you can write it that way if you want. All right. So, to go back to the Van Hoff, but now again we want to do it in terms of the concentration-based equilibrium constant. Yeah. Now we have an extra term. So this is me just taking the derivative of this.